Today I will talk about the crystal structures, and firstly maybe we should talk about a little bit about solids. Solids can be in the two types. So firstly amorphous, and the best example is the glass. In the amorphous phase, for instance, glass has no an ordered arrangement between the atoms. So there is no molecular order for the amorphous phases. And the other type, and the important one for us right now, is crystalline solids. And the example, a good example can be metals like gold, palladium, iron, and so on. Ordered structure. And the crystalline solids, we have so many ordered atoms, like on a layer. So this is the top view. We are looking from the top, and if we look at from the side, again we see something like this for this kind of structure. And if I want to take a very small cell from this structure, right, something like this, and also there is in the back, this becomes a unit cell. This is a unit cell. So the basic repeating structural unit of a crystalline solid is the unit cell. And this was the side view. So we have a unit cell. And each sphere represents an atom here, of course, or an ion or a molecule. And it is called as a lattice point. So if I want to draw this unit cell bigger, atoms are at the corners. And there is also an atom that we can't see. This is the simplest representation of a unit cell. And this is simple cubic structure. This is the simple cubic. And simple cubic, this the distance between this atom and this atom, these two atoms, is A, okay. And for instance, this is B, the distance between this atom and this atom. And there is also a distance between these two atoms. And this is C. A is equals to B and B is equals to C. And we have also alpha, gamma, and beta angles. And these angles equals to 90 degrees. If you want to look at the more than one unit cell, so or the connected unit cells, we have again atoms at the corners. I couldn't draw, I think this one. And I want to draw one more unit cell here. Okay, I will draw the simple cubic structure again. And look at this atom, okay? This is important atom. So it will connect to at least 2 more atoms. And this number of connection of atoms, so I'm just considering this atom. How many atoms does it has? So this is called as coordination number. So coordination number is defined as the number of atoms surrounding an atom or ion in a crystal lattice. So this is the coordination number. If we want to count it for this atom, it is 1, 2, 3, 4, 5, and 6. So our coordination number for the simple cubic is 6. This is the simplest representation, but we also draw a closed packing structure for the simple cubic. So these atoms has a connection or has a bond between them. There's a metallic bond if it is a metal. And I want to draw it in a zoomed version. And this is called as closed packing. We have a unit cell and the atoms are at the corner, but each corner has 1/8 of the atom. So this is the closed packing structure of our simple cubic. So at the corner, this is our corner, right? And if you look at the atoms at the corner in XYZ direction, we just only this part. So this is the 1/8 of the atoms. How many atoms do we have in this structure? 1 here, 2 here, 3 here, 4, 5, 6, 7, and there is also here. There is one more atom in here. I may not draw it beautifully, but there is also an atom here. So we have 8 atoms, but one atom has 1/8 of its volume, which means that we have only one atom in simple cubic structure. And if I draw the closed packing structures again, and I just want to look at one side, for instance here. And each corner includes one atom, as I mentioned, and this is the 1/8 of the atom. So the radius of atom is r. This is r. This length is also r, and this length is also r. And the 2r equals to h length. And this is the A. The total volume of the cube is A cube, or 2r third power. And the total atom volume is, we have one atom per unit cell, therefore 1/3 PR cube is the volume of the atom in the unit cell. So if you want to look at the ratio between the atom over volume, so total volume of the unit cell, this is the A cube, and the atom value is 4/3 PR cube, right? And the A cube was equals to 8R cube. R cubes will cancel, and this will be equal to 4 times 3 times 8. 8 will also cancel. This part becomes 2 and 1/6. We have also other types of cubic cells. The other one is body-centered cubic, or it is called as BCC. In body-centered cubic, we have a central atom, and we have the other atoms at the corners. So we have the atoms at the corners, and we have a central atom. So at the center we have another atom. As I showed, this is the only 1/8 of the atom, and we have 8 corners at the cubic cell. So we have one atom volume that comes from the corners, and we have one central atom. So BCC structure contains 2 atoms. And if we want to draw the close-packing structure, we have an atom here at the corner. It touches the central atom. This is the central atom. I don't want to draw it very big. And we have another atom here, and they touch to each other actually. But the corner atoms doesn't touch each other. Okay, and there is also another atom here. So I want to look at this plane. So this plane is something like this. This is the central atom, and these are the corner atom, 2 corner atom. Okay, and we have one more here. We have one more here. So the length of this part is again A, and the other length A times, and if you look at here, this part is X. Okay, I want to, so there's a Pythagoras here. So 2A squared is X squared, and X is equal to A square root of 2. So I can make a Pythagoras theorem here. And from here to here, I want to call it a C. And we can make a Pythagoras theorem here. A squared times 2A squared becomes C squared, and C becomes square root of 3A. And this C is also equal to 4R. Why? Since this part is R, this is R, this is R, and this length is also R. So A length in this case is equal to 4R over square root of 3. So I just want to teach the geometry of the unit cells. And in the last example, I want to show face-centered cubic or FCC. We have a cube again. But here we have corner atoms. And we have central atoms at the face. So this is the front view. And there are also atoms at the back. We have one corner atom here. And we have other 3 atoms on the planes. So we have again 8 corner atoms, and we have 1 over 8 of them. In each face we have half of the atom, and we have 6H in the cube, right? So we have 3 atoms here, and we have 1 atom that comes from the corners. This is the corners, and this comes from the faces. And the number of atoms in FCC structure is 4. So if you want to look at one of the sides, for instance here, we will see something like this. This is the A, and this is A again, and this part is 4A, 4R, or B. So B can be equals to 4R. Okay, I'm talking about this hypotenuse here. It is 90 degrees. So basically, A square times A square should be equal to 16R square, and the A should be equal to 8R, right? Square root of 8R. If you want to calculate the volume of the cube, it is A cube, or this square root of 8R cube should be volume of the cube. And this, all the atoms, simple cubic BCC structure or the FCC structure consists of only one type of atoms. So I am talking about, for instance, gold. Gold has a FCC structure, and if you want to calculate its density by using crystal structures, it is possible, and I will do it in the next video as an example. So I want to talk about the ionic crystals. And ionic crystals consist of ions held together by ionic bonds. The structure of an ionic crystal depends on the charges on the cation and anion end on their radii. So we have different ionic crystals. One of them is lithium sodium chloride that you use all the day probably. It has a FCC structure, so face-centered cubic. We have cesium chloride, and it has a BCC structure, and I can actually draw it very easily. So we have a cubic cell, and the central atom here. So this is a central atom, for instance cesium. If it is cesium, then the corner atoms is the Cl atoms, right? And the ratio between them is 1 to 1. So we have one corner atom in a unit cell and one cesium atom here. And the other structure is, for instance, zinc sulfide. So it is a zinc blend structure. It is a little more complicated. If I draw it here, probably you will not understand it, but I can put the some images that shows the crystal structure of these Ionic crystals. And we have calcium fluoride, and it has a different structure, fluoride structure. And Ionic solids have high melting temperature due to the strong cohesive forces, and ions have fixed positions in solid state, so do not conduct electricity. And these are the other important informations about the ionic crystals. And thank you for your attention.